Okay, section 2.4 is on rational models. What's a rational model or a rational function? Well, any function that has integer exponents is a rational function. And the type we're going to be looking at are non-polynomial rational functions. In other words, they will have a variable down in the denominator. Like, for example, this one has an x in the denominator, this one has an x squared. In this one right here, the 5x to the negative 1, a negative exponent reciprocates it. So this part of this right here is minus 5 over x, because the x to the negative 1 would flip it down the bottom. And when there's a variable down in the denominator, then it's a rational function. Now, if it was just a number in the bottom, like if this was 5 or a 5 squared or whatever, then that would not be a rational function that we're looking at here. It would just be a polynomial. A polynomial is a type of rational function, but the type we're looking at are the ones where there's a variable down in the denominator, because they have important things such as asymptotes. Okay, let's look at example 1. On this problem, you have to use the fact that distance equals rate times time. For example, if you were going 10 miles per hour for 10 hours, you would multiply the rate of 10 miles per hour times 10 hours, and you get a distance of 100 miles. So we can write this equation: distance equals rate times time. Your distance that you travel equals your speed times how much time you've traveled at that speed. If you solve this for r, we would divide both sides by t to get r equals d over t. And if we specified a distance, for example 100 miles, we would have this equation: r equals 100 over t, putting the 100 miles in there for d. Well, this is a rational expression right here. T is treated as the x variable, the independent variable, and it's down in the denominator. And if we look at what's going on here for this particular equation for different times, we get the following table. Like, for example, if t is 10, if you substitute 10 in here, 100 divided by 10 would be 10. In other words, it takes 10 hours to travel 100 miles if you're going 10 miles per hour. This is your rate right here. If we would substitute 20 in for t, 100 divided by 20 is 5. In other words, 20 hours, you'd have to go 5 miles per hour. And in 50 hours, if you had 50 hours, you'd have to average 2 miles per hour. And if you're going traveling for 100 hours, you'd have to go 1 mile per hour. And these are all calculated by just substituting these values for t in here. Well, the important thing is looking at the graph of these. If you look at the graph of these data points, which I have plotted here, you can see 10, 10 is right here and so on. Here's the points plotted. Here's 101. We can see that the more time you have, the slower you can go. And this graph will come down, getting closer and closer to this x-axis right here. And whenever that happens, that's called a horizontal asymptote. The graph gets closer and closer to some horizontal line. Whether the horizontal line is y equals 0, like it is in this case, or y equals 2 or whatever, it will never hit this. Like, for example, if you had 1,000 hours, you could go just 1/10 of a mile per hour on this. So this has a horizontal asymptote. Also, looking at this graph, if you have less and less time, here's your time axis right here. If you had less time, you would have to go faster and faster. So that this graph also has what's called a vertical asymptote. Okay, so as your time approaches 0 right here, your speed would have to approach infinity. And here, looking at the horizontal asymptote that we were talking about earlier, if your hours are approaching infinity, your speed could approach 0. So you hear these things a lot in these type of problems. Here's a second example. Toy manufacturer must spend $100 for setup costs and before he can start manufacturing a toy. Once the manufacturing is set up, each toy costs $1.50 to produce. It says write an equation to represent the cost of manufacturing n number of toys. Well, to make 0 toys, it costs $100 because that's the setup cost. Then for each toy after that, it costs $1.50. So for making 1 toy, it would be $1.50 plus the 100. 2 toys, it would be 2 times $1.50 plus the 100, which is $103. The equation for this is it's going up linearly. It's going up $1.50 each toy that's produced. So there's $1.50 for each n right here, plus the $100 setup charge. So the cost is equal to $1.50 times N plus $100. That's a linear equation. Now in part B, it says write an equation that represents the average cost. Well, the way you get an average cost is divide the cost by the number of items produced. So here's the cost function right here, 1.5n plus 100. And divide that by n, the number of items produced, and that gives you this C bar right here, which stands for average cost. Well, this average cost function right here is a rational function. So now it says, what is the average cost approaching as the number of toys produced gets larger? So now what we're looking for is as n gets larger and larger, what is this thing right here approaching? The C bar, the average cost. Well, if I put 0 in, I get division by 0. If n is 0, no toys produced. Well, that would be 1.5 times 0, which is 0, plus 100, which is 100, divided by 0, and division by 0 is undefined. We want to know, though, what happens as the number of toys produced approaches infinity, gets larger and larger. Well, if you put 1 in, you get 1 times 1.5 plus 100, which is 101.5, divided by 1, which is 101.5. Making 10 coins and 10 toys, and substituting then, you get 11.5. 100, you get 2.5. 1,000, if you substitute it in, you get 1.6. And if you substitute in larger and larger numbers, you can see it's getting closer and closer to 1.5. Now, you can use an Excel sheet called the rational sheet to evaluate these. And let me go ahead and do that. So on the rational sheet, this is the rational sheet here, you can see you can put up to a cubic over up to a cubic. And on this particular equation here, and it's right here, you can see we have no cubic and no square term, but we do have a linear coefficient of 1.5. So we need to go down here to see, it tells you what each thing stands for here. And if we go down to the D area, we can put in the 1.5 right here, and then right here is the 100, and then over here you put in your coefficients of your denominator, and the only thing in the denominator is a 1 for a linear term. Okay, and now we have the graph of this is right here. And the reason it looks this way is because when we put in 0, we got undefined, and that is giving us a vertical asymptote right here. That's why the graph is going straight up right here. And then it looks like it's leveling off right here, and that would be your horizontal asymptote. But we can put in values for x right here, like if you put in 0, you get division by 0, which is what we had. And like let's put in 1, you get 101.5. Let's go up to 100. There's the $2.50. Let's go to 10,000. And you can see you get $1.51. And the larger this goes, like if I put in 1,000,000, I get 1.5001. Well, it's getting very, very close to $1.50. So the answer to this question, the question was, what is the average cost approaching as the number of toys produced gets larger? Well, that would be $1.50. And that's the answer to that problem right there. And we'll stop this video right here.